This is the Parallel AI tutorial for modeling and running an optimization problem, in this case a scheduling problem on the Parallel AI backend system using the Parallel AI SDK. I do want to mention though that this is one of the few tutorials that we are providing using the Parallel AI SDK, because we are currently moving everything towards the GUI approach, and indeed this is what we are implementing and what we are suggesting to use, the GUI. The reason is that with the GUI you can accomplish much more, much faster. To give you a little bit of context, everything in Parallel AI is modeled as a network of autonomous intelligent agents that they make some optimization decisions. And you see that with the GUI, with the user interface, it's much simpler to model these scenarios. For example, this is an agent for a routing system, and then you can model the event graph, so the events that are going to trigger the optimization on the agent. So for the scheduling, you will have a scheduling agent, and you double click on it, and you open an event graph window where you can set all the events. For example, if you want to trigger when you deploy the system, if you want to trigger the agent to run the optimization model after an API request, well, you can put an API event here, and then you connect these blocks and you can set different parameters. And there are other scenarios, for example, where you want to model the behavior of the agent. When do I re-optimize? Well, that is modeled with behavior trees, which is an interesting AI technique that is very nice to be used with a graphical user interface, because you actually connect blocks, right, creating a tree, and you see how the behavior runs in real time, which would be much harder to see or to do with an SDK. And there are on Parallel AI YouTube channel some videos I'm creating a tutorial about how to use the GUI here. But with that being said, we can close this up and close this down and start with the SDK example. So when you open the files that we are going to send you to try to replicate the same things that I'm doing now, we are going to see a folder something like this, where you have the scheduling model, and we are going to use here the Python notebook. So you see the scheduling model here. This is the one that I'm going to use now in this video, and then the README, where you see the instructions how to install the environment, and then some other examples here you can try if you want. There are genetic algorithms and routing, scheduling, and other things. The instructions, the documentation for the mathematical programming toolbox, and some data here. Here now, let's start by looking at the README. This is nothing scary. This is all Python related. It's nothing related to Parallel AI, and it's like standard things that probably you already know, right? So install an environment, install the Parallel SDK. This step here is going to take a little bit, so be patient and run the notebook, right? If you like to use the notebook. Very well. So let's start with. Assuming that you already follow the README. If you encounter some problems, please do write me, and I'm going to answer right away to help you out to install the SDK. Hopefully you shouldn't experience any problems with that. So when you open the notebook and you open the example, you're gonna see something like this. And let's go through this example together and see how you can model a scheduling problem with the Parallel AI SDK. Very good. So the first thing that we need to do is to import the libraries for the scheduling toolbox, because we're going to solve a scheduling problem. So that's very simple. Scheduling toolbox import. So let's go ahead and run it. And then we want to get the scheduler for the scheduling, for solving the scheduling problem. So it turns out that every toolbox has its own scheduler. Scheduler is the engine that optimizes the problem to solve, right? So in this case, we have a scheduler, and we can build that with the build job show scheduler API call. Now, for different problems, there are different schedulers, as I said. So, for example, the scheduling toolbox has other use cases like employee schedule, right? You want to determine the schedule of a group of people, so you're going to build an employee scheduler. In this case, we want to solve a job shop problem, so we are going to create a job shop scheduler like this. Now, each scheduler, in turn, has its own model. So you want to get the model from the scheduler and fill the model with your data, and then solve the model running the scheduler on the backend system. So in this case, we get the instance, all right? And then we can set some parameters here. In this case, we start with the search timeout in seconds, 10 seconds. What this means is that the backend system is going to run for the specified amount of time, so in this case 10 seconds, and returns either no solution, or it returns the solution that it found it within the time limit, right? So I want to be super clear about this, because in this version of the SDK of Parallel AI, we don't run for the scheduler an anytime algorithm, which means we don't run an algorithm that at any point in time it gives you the best solution found so far. Instead, we run a complete search algorithm, meaning that if you find something within 10 seconds, you get the optimal solution. If you don't find anything, you don't get anything, right? There are other things that we are now implementing, like local search and heuristics. So these kind of algorithms, large enable search, another one very good for this problem here. For this kind of algorithms that you can specify with the API, not in this version, you will be able to stop the search and interrupt the search at any time and get the optimal result found so far. In this case, you get only the result if that can be computed within 10 seconds. If you don't specify anything, it runs forever until it finds a result, right? Number of parallel cores. This is something that depends on the backend system that you're going to use. For in this case, you're going to be connected. This is an open. I'm going to show you later. This is our open IP to a small instance that has only one core. But that's not the case in general, right? When you actually subscribe to the system, you can select the different number of cores, different number of instances. In this case, you can set up the number of cores you want to use, because it turns out that the backend system can run in parallel as well, right? You can span up multiple threads to perform search in parallel and speed up the process. So in this case, since we have one core, I set up only one here, and this is also the default value. And this is also interesting, the consistency search. So you can decide whether you want to just find if the schedule, if the data lead that you set for your model leads to a problem that can be solved, right? If there is at least one solution, or if you can decide if you want to find the optimal solution. So why you can do that? Well, it turns out that if you're only interested to see if there is a solution, that usually is much faster than finding the optimal one, right? And to do that, you can set consistency search to true. So when you set this to true, you're going to find only if there is a solution. In this case, we want to find the optimal solution, so I set it to false. Now, by default, this is false. So by default, you're going to find the optimal solution always. Here we set the cost per time unit, and we are going to find the make span. We want to optimize the make span, so which is the maximum length. We want to minimize basically the total length of the scheduling the scheduling process, right? So. And we can set up here a cost per time unit. I set 1, so we have basically 1-to-1 mapping here. Very well, so let's go ahead. And now, as you know, a job shop is modeled by defining two main things, which are machines. So they're the machines that we want to operate on, and jobs, right? So we start with machines. Here now, very simple things. I create only one machine. You can create n machines, how many machines you want. So you see that here I call the instance, right, JS, add machine. I give my ID, and be careful here. You need to give a unique identifier for each machine. Otherwise, the scheduler, the instance says no, there is an error, right? So you need to provide a unique identifier. And if you want a name, it's not necessary, but you can provide a name, so you can look up the machine later. And then another thing, this is not necessary, but you can do it. You can put the availability for the machine, right? So you can say my machine works only between 32 and time 54. Now, another thing to notice is that we are, in this case, solving a problem where we have finite domains, right? So we cannot use real numbers to set up the times. This is not a limitation, though, because you can always multiply your real numbers by an integer, so you can take you can scale them up, right? So if you have like a 0.5 or you have 3.2, well, you multiply by 10, you have 32 and 54, and then the result you multiply them back for you divide them back, right? So in this case, we say that we have a machine that is available between time 32 and 54. These two random numbers, right? So let's create it. And now, basically, the model has a machine inside. And then you can query, of course, the model with JS. I do JS dot get machine here. I'll get all machines, get machine, and you can pass the identifier of the machine and get the machine, right? But let's go ahead and create the jobs. Similar thing. Here you have jobs. I think a note about jobs, right? So the unit that gets scheduled on a machine is a job. A job is a sequence of tasks. You can put inside a job, we can specify one or more tasks. These tasks are executed sequentially within a job. Okay, so we have jobs, and jobs are defined by tasks. So in this case, we create one job, again the ID and my name here of the name of the job, right? And we said we need to have at least one task that defines the job. So we create a task like this, and then we can specify some requirements for the task. So for example, we can say that this task here in particular, the one we just created, needs to run on a specified machine. And in my case, this machine is this machine that we created here, right? So machine that I have it here, get ID, or you can also pass machine ID, whatever you prefer here, but so you specify where this task has to run. And then you can specify the duration of the task, right? So you say this task is the duration is 10. Again, if it was like a number like I don't know 0.5, you multiply that by 10 and you obtain 5, right? So let's go ahead. So now I have machines, I have jobs and tasks. Now the interesting part here, we want to connect to the backend system. Okay, so this defines your instance. Now you have to run the instance on the Parallel AI backend. When you do this, you're going to connect to the using the Parallel client. You see here when we import this, basically when you work on this, you work on the Parallel client. So you want to connect the Parallel client to this IP here, or an IP. You can ask us for an IP. These are all free IPs that we open up, and they are connected to less powerful instances, and they are used for you to try out the system, to see how it works and to play with it a little bit. So you connect, you create an optimizer by connecting the Parallel client to the IP, and the optimizer is the actual thing the thing that receives the model and takes care of sending it to the backend system and then calling it back, the results, and so on. So the optimizer is the one that is optimizing and doing all the communication with the backend system. So let's go ahead. Very good. So now it's connected to our backend system, and now what we want to do is to run the optimizer right on the backend. So here I pass the scheduler. Be careful here. You see the scheduler we created here. I don't pass the instance itself. I pass the scheduler. So the scheduler is an instance, right? We specify the instance, and now we pass the scheduler to the optimizer, so the optimizer can optimize the scheduler. Okay, so this is going to send the scheduler to the backend system. The backend system is going to process the scheduler, find the solutions and everything. And here you see that I have run optimizer sync, which means that I run this synchronously. So I wait, this is a blocking call to wait for the scheduler to finish. There is also an async version where you can just send it and get back the results do other stuff and get back the results asynchronously. But in this case, I'm going to run it synchronously. So you see that all this thing here now went to the backend system, and it gives you some information. Once it is completed, right? And you see the engine creation, how long it took on the backend to create the engine. Nothing, because the model is very small, right? The same thing for loading the model, it was very small, and it took 2 milliseconds to optimize it. Very well. And then once you're done, you can disconnect to the back. You don't need to be. You can be connected, but just even if you close the whole thing here, it's going to disconnect automatically. But just for consistency, it's better to disconnect. So you deregister basically your scheduler from your optimizer from the backend system. And you don't need to do these two things here, right? You can do this at the beginning, just right as soon as you import all the packages, and then at the end, so you're all set. So very well, you disconnected, and now we can explore the solution, right? So now we have our things here. Well, let's think one thing at a time, right? So let's say that we want to, for example, find the status, right? After everything run here, we want to see, do we have a good solution? Do we have a valid solution, or do we find a solution, right? So we can just query from our instance. Now, when you return from this call here, this the optimizer and the scheduler set up all the information on the instance, right? So now the instance is updated, and let's see the status of my model. What turned out to be. Success, which means that the backend system was able to find a solution. And now we can also query the make span, right? So let's another one here. Let's print here, and we can see the optimal value of this, right? 42. And why 42? Well, and why is pretty simple, right? We just defined here that the machine is available from time 32 to 54, and the duration of the task is 10. So 32 plus 10 is 42. So the total make span, how long it's gonna take to run all my tasks, is 42, right? We only one task that is like last 10 units of time. Of course, now you can also let me delete these things here and print, for example, get all the machines and all the jobs, and you can print all the solutions. So with this, you can get all the machines, and then you can print the solution, and then you can keep working on it, right? You can do some stuff with the machine. You can query what tasks are on the specific machines. You can query all the jobs, and you can also print the solution from the JS, right? Get the instance. This is the JS that we have above here. You can print directly the solution as a string, and you see that this is a solution, right? This is the name of the model, and we have only one machine one. Name is my machine, and is this what is scheduled on the machine, right? In this case, we have the task with ID 1 that starts at the time 32 and finish at 42. Very well. So this is what I wanted to show you. Now you can start playing with this by adding more machines, adding more constraints, adding specifying make span, cost per time unit. Now this is a very simple kind of mock problem where you have one machine and one task, right? But you can put all the machines that you want and all the tasks that you want and run it on the backend system, get better results. What I recommend to do is to try incrementally with a time limit, right? So you say, I try with this model and I try with a time limit of 15 seconds and see if it can be solved within 50 seconds. If so, you can maybe increase the complexity of the model and so on, right? Very well. So this is all that I want to show you here. In the folder that you receive, you will have the same model here. Plus you're gonna have other experiments, other models to try out, and just play with it. If you have any questions, feel free to reach us out. I'm going to help you with your model. I'm going to help you explaining better if you didn't understand the whole process here, and enjoy the ride. Thank you.